Good day, everyone. Welcome to today's lecture on vibration and noise control, specifically focusing on vibration isolation. My name is Dr. C. Sendamarikannan, and I am Associate Professor in the Department of Mechanical Engineering at SVC. Today, we are diving into crucial aspect of mechanical engineering, how to effectively isolate vibrations. Vibrations, as you know, are ubiquitous in machinery and structures. They can lead to a multiple of problems from reduced performance and premature wear to increased noise and even structural failures. Therefore, understanding and implementing effective vibration isolation methods is paramount. Well, we begin by defining what vibration isolation truly means and why it is so important. We will explore the fundamental principles behind it, including concepts like natural frequency, damping, and transmissibility. Then, we will delve into the various methods employed for vibration isolation. Think about your daily life. Your experience, you are experiencing vibration isolation in action every time you travel in a car. The suspension system, essentially a spring and damper, isolates you from the bumps and ups and downs of the road. We will be looking at similar principles but in a more detailed and engineering context. We will also some practical consideration involved in selecting the right isolation method for a specific application. Factors like the frequency of the vibration, the weight of the equipment, and available space all plays a crucial role. We will look at some real world examples to illustrate all these points. By the end of this lecture, you should have a solid understanding of the principles and methods of vibration isolation and be able to apply this knowledge to solve practical engineering problems. So, let's get started with understanding the fascinating world of vibration isolation. I already discussed that is, this lecture is part of our Unit 2, that is the second half of the Unit 2. We are having the titles vibration isolation method, and dynamic vibration observer. Today, in this lecture, we are going to see about vibration isolation and isolation methods. In the next lecture, we are going to see about vibration absorbers. That will be the last lecture in the Unit 2 series. All right, let's continue our discussion on vibration control. We will talk about the importance of isolating vibrations, but now we will look at a broader picture. How do we control vibrations in general? So we are talking about some important methods to control the vibration that are: first, we have control the natural frequency and avoid resonance under external excitation. Now, the resonance occurs when the frequency of an external excitation matches this natural frequency, leading to large amplitude vibration. So, controlling natural frequency, essentially tuning the system, is crucial to avoid resonance. This might involve changing the stiffness or mass of the system. Next, we introduce damping mechanism to prevent excessive response of system. Damping, as we have discussed, is the dissipation of energy. By introducing damping, we can reduce the amplitude of vibrations, particularly near resonance. This can be achieved through various means like using materials with high damping properties or introducing mechanical dampers. Then we use vibration isolators to reduce transmission of excitation forces from one part of the machine to another. This is where our previous discussion on vibration isolation comes in. Isolators act as barriers, preventing the transfer of vibration from the source to other parts of the system or to the surrounding environment. And lastly, add an auxiliary mass neutralizer or vibration absorber to reduce response of system. This involves adding a secondary mass system, that is tuning system, to specific frequency to counteract the primary vibration. Is a clever way to absorb energy and reduce vibration at some specific frequency. In essence, this method aims to shift the natural frequency away from excitation frequencies to introduce damping to dissipate energy or blocking the transmission of vibrations or actively control them. Each method has its own advantages and disadvantages. Choice depends on the specific application and requirements. Now, delve deeper into one of these methods. Perhaps you focus my lecture. Now, let's focus on a very specific and critical aspect of vibration control, managing the natural frequency of a system. As we have seen, resonance is a major concern. First, we see the consequences of resonance. Resonance leads to large displacement, which in turn result in large strain and stresses, ultimately leading to the failure of the system. This is very crucial. It's not just any annoying vibration, it is about potential catastrophic failures. Often, the excitation frequency of the external force causing the vibration is something we can't able to control. Think of a machine operating at a fixed speed or a building subjected to seismic activity. We can't change the earthquake and we may not be able to change the machine's operating speed. Therefore, we must control natural frequency by varying the mass or stiffness to avoid resonance. If we can't change the excitation frequency, we must change the natural frequency of the system so it doesn't coincide with the excitation. However, practically, mass cannot be changed easily. Changing the mass of a large structure or complex machine can be very challenging or even impossible. Hence, let's conclude it. That is, we can change only stiffness by altering the material or number of springs or the location of bearings. This is the most common approach. Stiffness can be modified by selecting different materials with varying elastic moduli or by altering the structural design such as changing the number or placement of bearings or springs. Essentially, we are aiming to shift the natural frequency away from the excitation frequency while changing the mass, even though it is theoretically possible. Altering stiffness is often the more practical and feasible solution. This might involve material selection, structural modifications, or changes to support systems. We have discussed controlling natural frequencies to avoid resonance. Now let's look at another crucial method, introduction of damping. The system may be required to operate over a range of speeds, hence cannot avoid resonance. This is a significant challenge. If a machine or system operates at various speeds, it is likely to encounter its natural frequency at some point. In such cases, simply shifting the natural frequency might not be sufficient. Hence, we can use material with high internal damping to control the response. Materials with high damping properties dissipate energy more effectively, reducing the amplitude of vibrations, particularly at resonance. Example, rubber materials or some certain polymers. The next method is, can we use bolted or riveted joints? Yes, we can use bolted or riveted joints to increase damping. This might seem counterintuitive, but it is a practical approach. The bolted or riveted joints permit slip between surfaces and dissipate more energy compared to welded joints. The friction between the surfaces in these joints convert vibration energy into heat, effectively damping the vibrations. However, there is a trade-off. They also reduce stiffness of the structure, produce debris, and cause fritting corrosions. Bolted or riveted joints are not as rigid as welded joints, potentially reducing the overall stiffness. They can also generate debris due to wear and tear, and fretting corrosion can occur due to the relative motion between the surfaces. So, introducing damping is very crucial when resonance to be avoided. We can achieve this through material selection or by incorporating specific joint designs. However, it is essential to consider the trade-offs, particularly potential reduction in stiffness and the risk of debris and corrosion. Now, let's get a bit more technical and look at the mathematical representation of damping. This slide presents the equation of motion for a single degree of freedom system with internal damping under excitation. We see the equation ms double dot plus k times 1 plus I eta times x equals phi naught e to the power of I omega t. Let's break this down. Here, m represents the mass, double dot is the acceleration, k is the stiffness, eta is the loss factor, x is the displacement, f naught is the amplitude of the excitation force, omega is the excitation frequency, and it is the time. The key term here is 1 plus eta. The complex term represents the stiffness with internal damping. Eta, the loss factor, is a measure of the damping in the system. It is defined as energy dissipated during one cycle of harmonic displacement per radian divided by the maximum strain energy in the cycle. This slide shows the amplitude of response at resonance. We see that amplitude of response at resonance is proportional to f naught over k eta or f naught over a e eta, where a is a constant. This equation tells us that the amplitude of vibration at resonance is inversely proportional to the loss factor eta. Simpler terms, higher damping leads to lower amplitude vibration at resonance. This is a crucial component in vibration control. So, in this slide, the mathematical framework for understanding damping in a single degree of freedom system, we have seen the loss factor eta is a key parameter that quantifies the damping, and it directly affects amplitude of vibration at resonance. Now, let's delve into a specific type of material that particularly effective for providing internal damping, that is viscoelastic materials. The viscoelastic materials have larger values of eta and are used to provide internal damping. Remember, the eta are used to provide internal damping. Our loss factor it is a measure of damping. Viscoelastic materials like rubber or certain polymers have a high loss factor. meaning they dissipate a significant amount of energy when deformed. However, there is a trade-off. The disadvantage is the properties change with respect to temperature, frequency, and strain. This is crucial consideration. The damping properties of the viscoelastic materials are not constant. They vary depending on the operating conditions. This can limit their effectiveness in applications with wide temperature or frequency ranges. To address some of this limitation, we often use sandwich viscoelastic material between elastic layers and constrained layer damping. This technique involves bonding a layer of viscoelastic material between two stiffer elastic layers. This constrained layer configuration enhances damping performance and increases material stiffness. Finally, the material with largest eta will be subjected to a smaller stresses. This means that the material with the high damping capacity will experience least amount of stress during vibration. This can be a significant advantage in applications where stress reduction is very much crucial. And so, viscoelastic materials are excellent for providing internal damping due to the high loss factor. However, the temperature and frequency sensitivity requires careful consideration. Constrained layer damping is the technique used to enhance the performance. And remember, higher damping leads to lower stress in the material. Now, let's shift our focus to a practical and widely used method for controlling vibrations, vibration isolation. Here, we are going to introduce the basic concept and some common examples. The core idea behind vibration isolation is simple. It is we are going to have some kind of isolation between the vibrating element and with respect to the machine elements or some other structures. So we are going to insert isolators between vibrating mass and vibrating source to reduce the response. Essentially, we are placing a barrier between the source of the vibration and the component we want to protect. Passive isolators, springs, cork, felt, etc. These are common examples of passive isolators. They don't require external power or control systems. Springs, as we discussed, provide flexibility, while materials like cork and felt offer damping. For example, mounting of high speed punching press. Here it is given in this diagram. A punching press like the one which is shown on this figure generates significant vibrations. By mounting it on isolators, here you can see the isolators, we can prevent the vibrations from being transmitted to the surrounding structures, protecting the building and nearby equipments. And we are also able to see different types of isolators here. You can see the spring-based isolator as well as other types of isolators which uses elastomers and or other materials. So vibration isolation is about interrupting the path of vibration transmission. Passive isolators like springs and damping materials are commonly used for this purpose. Mounting of a punching press is a great example of this technique is applied in practice. We have discussed passive vibration isolators. Now let's turn our attention to active isolators, which offer a more sophisticated approach to vibration control. This slide also introduces the concept of transmissibility, a key metric for evaluating isolator performance. Let's see. The active isolators comprised of servo mechanism with sensor, signal processor, and actuators. Unlike passive isolators, active isolators use a feedback control system. A sensor detects the vibration, a signal processor analyzes it, and an actuator generates a counteracting force to cancel the vibration. The effectiveness of an isolator, whether passive or active, is often quantified by its transmissibility. The effectiveness given in terms of transmissibility is the ratio of amplitude of the transmitted force to that of the exciting force. In simpler terms, it is the ratio of how much vibration gets through the isolator compared to how much vibration is applied. A lower transmissibility means better isolation. First, what we have to do, protect base of vibrating machine against large unbalanced or impulsive forces. This is similar to our earlier example of the punching press. We are protecting the foundation from the vibrations generated by the machines. Again, you can protect system against motion of its foundation. This is opposite scenario. We are protecting a sensitive system like a precision assist systems or instruments from vibrations coming from the ground or the supporting structures. So, active isolators offer superior vibration control through feedback systems. Transmissibility is a crucial metric for evaluating isolator performance with lower values indicating better isolation. And finally, vibration isolation can be used to protect either the base of a vibrating machine or sensitive system from foundation vibrations. Here in this slide, we are going to see two primary scenarios that we encounter in vibration isolation along with the corresponding mathematical expressions. Let's start with the first scenario as given in the figure A. Protect base of vibrating machine against large unbalanced or impulsive forces. Here we have a vibrating machine represented by mass M mounted on a base. The machine is generating vibrations and we want to prevent these vibrations from being transmitted to the rigid base or foundation. You can see the spring damper representing the isolators between the machine and the base. Hence, from the equation, we can see that is Fi F sub I of t equals Kx of t plus Cx dot of t describes the force transmitted to the base. This force is a function of the displacement x and velocity x dot of the machine as well as stiffness and damping of the isolators. Now let's look at the second scenario. Protect the system against motion of its foundation. In this case, we have a delicate instrument or machine also represented by mass M mounted on a base. However, this time the base itself is vibrating represented by Y of t. We want to protect the instrument from these base vibrations. Again, we have a spring damper acting as the isolators. In this, the equation f of t equals mx double dot of t, which also equals k times bracket x of t minus y of t plus c times bracket x dot of t minus y dot of t describes force acting on the instrument. This force is a function of the instrument's acceleration, displacement and velocity as well as the base displacement and velocity. What is the key difference? The key difference between these two scenarios is the source of vibration. In the first case, vibration originates from the machine itself. In the second case, vibration originates from the base. The equations reflect this difference, showing how the forces are related to the displacements and velocities in each scenario. So, from this slide, we are getting two fundamental problems addressed by vibration isolation and provides the mathematical framework for analyzing them. Understanding these two scenarios and the equation is very crucial for designing effective vibration isolation systems. Here in this slide, we are going to see fundamental vibration isolation system specifically focusing on a scenario with rigid foundation. The title clearly states vibration isolation system with rigid foundation. This means we are dealing with a system where the foundation or base is assumed to be perfectly rigid and doesn't move or deform. The, here you can see that the resilient member placed between vibrating machine and the rigid foundation. This is the core concept of vibration isolation. We are introducing a flexible element, a resilient member between the vibrating machine and the rigid foundation. This element will absorb and dampen the vibrations. Here, the next thing, member is modeled as a spring and a dashpot C as shown in the second figure. We are simplifying the resilient member into a spring dashpot model. The spring K represents stiffness of the member, while the dashpot C represents its damping properties. We can see a simplified representation with just the resilient member block. So from this, we can able to analyze the system by mathematically modeling the vibration isolations. We can also use the equations of motions to determine how the vibrations are transmitted through the resilient member and to the foundation. By selecting appropriate stiffness damping values, we can minimize the transmitted vibrations. So from this slide, I introduces you a fundamental model for vibration isolation with rigid foundation. We used a resilient member modeled as a spring and dashpot to isolate vibrating machine from the foundation. This model allows us to analyze and optimize the system for effective vibration control. Building on our previous discussion, let's delve into the mathematical analysis of this vibration isolation system. This slide presents the equations that govern the system's behavior. Let's see. Here we are going to derive transmitted force by writing the equation of motion first. Our primary goal is to find out the transmitted force, and that is to be minimized such a way that isolation should be perfect. The equation of motion is given by mx double dot plus cx dot plus kx equals f naught cos omega t. This is a standard second order differential equation representing forced vibration of a damped system. Here m is mass, c is damping, k is stiffness, and f naught is the amplitude of the forcing frequency and omega is its frequency. Let's see the solution for this equation, which will be given in the form of x of t equals x cos omega t minus pi. This represents the long-term behavior of the system after any transient effects have died out. The x is the amplitude of the steady-state vibration and pi is the phase angle. This slide then provides for expressions x and pi is equal to f naught divided by the square root of bracket k minus m omega squared bracket squared plus omega c squared. Pi is equal to arc tangent of omega c divided by k minus m omega squared. These expressions are derived from the equation of motion and are crucial for understanding the system's response. The force F of t transmitted to the foundation is given by F suffix t, of which equals to k of x of t plus c x dot of t, which is further can be expressed as k x cos omega t minus pi minus of c omega x sin omega t minus pi. This equation shows that the transmitted force is a function of the displacement and velocity of the mass as well as the stiffness and damping of the isolators. Finally, the magnitude of total transmitted force F of t, which is given by F suffix t, equals to the square root of bracket k of x bracket squared plus cx dot bracket squared, which can be further simplified to x times square root of k squared plus omega squared of c squared. Substituting the expressions for x, we finally got f naught times the square root of k plus omega squared divided by square root of bracket k minus m omega squared plus omega squared of c squared. This final equation is crucial because it shows how the magnitude of the transmitted force depends upon the system parameters like mass, stiffness, damping, and excitation frequency. By manipulating these terms or parameters, we can minimize the transmitted force and achieve effective vibration isolation. I conclude in this slide that is the mathematical framework for analyzing the vibration isolation system we derived, the equation of motion, steady state solution, transmitted force expressions allows us to understand and predict the system's behavior. By understanding this relationship, we can design effective vibration isolation systems. Now let's introduce a crucial concept for evaluating the effectiveness of our vibration isolation system, that is transmissibility. Here we can see how it is defined and how it relates to the frequency ratio. Let's see. That is, transmissibility is nothing but reduction of force transmitted to foundation, which is remaining as our very primary goal. That is, we want to minimize the force transmitted to the rigid foundation. The key concept here is once again transmissibility denoted by T suffix R, that is defined as the ratio of force transmitted to the foundation to the force applied to the machine, or F naught. Now we can substitute whatever we derived in the previous slide, that is F of t and F naught. From that we can able to simplify the terms further by substituting R, the ratio of forcing frequency by natural frequency, that R we can substitute, and finally we can able to get the expression of transmissibility in terms of psi and R. Now the next slide we can able to see how this transmissibility is varying with respect to this ratio of forcing frequency to the natural frequency. Now let's analyze the graph of transmissibility. This is with respect to transmissibility in y-axis and frequency ratio in x-axis. This graph is crucial for understanding the performance of our vibrating isolation systems. As you can see, the graph plots transmissibility on the vertical axis and the frequency ratio are on the horizontal axis. We have three curves representing different values of damping, that is first one zeta equal to 0, second one zeta equal to 0.25, and the third one zeta equal to 0.5. The graph is divided into two regions, the amplification region and the isolation region. In the amplification region, where it is T suffix R is greater than 1, meaning the transmitted force is greater than the applied force. In the isolation region, where T suffix R is less than 1, meaning the transmitted force is less than the applied force. Let's start with the curve for zeta equals 0, which represents no damping. You can see a sharp peak R equals to 1, which indicates resonance. At resonance, the transmissibility is very high, meaning the transmitted force is much larger than the applied force. This is undesirable for vibration isolation. Now, let's look at the curve for zeta equals 0.25 and 0.5. As you can see, the peaks are lower and broader. This shows that damping reduces the transmissibility at resonance, broadens the range of frequencies where isolation is effective. Higher damping leads to lower transmissibility at resonance and wider isolation region. The vertical line at R equals square root of 2, which is very much significant one. This is the point where T, that is transmissibility, equals to 1. For R values greater than square root of T, we are in the isolation region. This means that for effective vibration isolation, we want to operate in this region where the excitation frequency is significantly higher than that of the natural frequency of the system. You can also observe that higher damping shifts points where T suffix R equals to 1. This means that with higher damping, we can achieve isolation at lower frequency ratios. So this graph clearly illustrates the importance of damping in vibration isolation. Higher damping reduces transmissibility at resonance and broadens isolation region. For effective isolation, we want to operate in the region where R is greater than the square root of 2, and higher damping allows us to achieve this is at lower frequency ratios. In this slide, we are seeing the relevant equations and definitions, which is with respect to reduction of force transmitted to the mass, that is vibration isolation system with rigid foundation. However, this time we are focusing on the displacement of the mass rather than the force transmitted to the foundation. The equation mz dot plus cz dot plus kz equals minus y double dot I of m, where z equals x minus y, describes the motion of the mass related to the base. The key concept here is displacement transmissibility, denoted by C suffix d. Is defined as the ratio of amplitude of the mass displacement to the amplitude of the base displacement. Displacement transmissibility tells us how much the mass displacement is amplified or attenuated related to the base displacement. A value of T suffix d less than 1 means mass displacement is smaller than the base displacement, indicating effective isolation. Here we can also see that the ratio of the maximum steady state acceleration of the mass and the base. This is an important point. Displacement transmissibility is directly related to the acceleration transmissibility. Minimizing displacement transmissibility also minimizes acceleration transmissibilities, which is often crucial for protecting sensitive equipments. What is the key takeaway? So, we introduces the concept of displacement transmissibility, which is crucial metric for evaluating vibration isolation effectiveness in terms of displacement and acceleration. The equation for T suffix D highlights the importance of the damping ratio and the frequency ratio in achieving effective while isolations. Now, let's look at the specific equations used to determine the necessary parameters for isolating a vibrating source from its surroundings. Here we are presenting some set of formulas to use for that purpose. Here we are going to see that the isolation is going to be the purpose of to isolate complete vibration from its surroundings. So to determine these conditions, to minimize the transmission of vibrations from a source to its environment, we need very important parameters like stiffness, damping, and pi. First, let me see the first equation which gives an approximation for the transmissibility, that is T suffix R is approximately equal to 1 divided by square minus 1. For R greater than square root of 2 and small zeta values, R is the frequency ratio and zeta is the damping ratio. This formula is further simplified and represented here, that is the R defines as omega and omega ratios, that is forcing frequency divided by the natural frequency. Further, we can able to create in terms of RPM, that is rotational speed in revolutions, that is delta suffix T, that is del static, which is very important parameter, and G is the acceleration due to gravity. What is the significance? We are seeing so much of mathematical equations. The significance is the variable R represents isolation efficiency, that is defined as 1 minus T suffix R. It tells us how much the vibration is being reduced. Higher value of R indicates better isolation. Finally, the slide provides an equation for N, the rotational speed in RPM. N is equal to 30 divided by pi multiplied by the square root of G by delta multiplied by the square root of 2 minus R divided by 1. Further, which is simplified and equals to 29.9 multiplied by the square root of 2 minus R divided by delta suffix T minus R, which is very important equation to determine the record static deflection or the rotational speed for a given isolation efficiency. By manipulating all these parameters what we seen in this slide, which will be very much useful effectively to reduce the transmission of vibrations. This chart is powerful tool for designing vibration isolation systems. It relates the excitation frequency, static deflection, and the resulting performance in terms of magnification or percentage reduction. The chart plots excitation frequency N in revolutions per minute or cycles per minute on the vertical axis, static deflection, that is del static, on the horizontal axis. We have two scales for static deflection, inches on the top and millimeters on the bottom. The diagonal line represents the lines of constant performance. The lines labeled with percentages 98, 97, 95, etc. indicate percentage reduction in vibration. The lines labeled with the numbers 2, 3, 1.5, etc. indicate magnification of the vibration. The line labeled resonance with natural frequency represent conditions where the excitation frequency matches natural frequency of the system. The operating frequency which is near this line should to be avoided as it leads to large amplitude vibrations. Let's say we have a machine operating at 2000 RPM and we want to achieve 90% reduction in vibration. We can locate it, that is 2000 RPM, on the vertical axis, follow it horizontally and intersect at 90% reduction line. Then we drop vertically to the horizontal axis to find the record static deflection. In this case, it is approximately 0.02 inches or 0.5 millimeters. If we want to know the magnification for a given static deflection and excitation frequency, we follow the same procedure. For example, if we have a static deflection of 0.005 inches and an excitation frequency of 1000 RPM, we find the magnification is approximately 1.2 times. This chart allows us to quickly determine the record static deflection for a given excitation frequency and desired performance. It's a valuable tool for selecting appropriate isolators and designing effective vibration isolation systems. Now let's look at the specific case where isolating a vibrating source from its surrounding when the vibration is caused by rotating unbalance. Here we are presenting the relevant equations for force transmissibility for this scenario. That is, isolation of source of vibration from surroundings and reduction of force transmitted to the foundation due to rotating unbalance. We are specifically looking at vibration caused by an unbalanced rotating component. The excitation force is given by f of t equals f naught sin omega t, which is further expressed as m e omega squared sin omega t. Here, f naught is the amplitude of the force, omega is the angular velocity, m is the unbalanced mass, e is the eccentricity of the unbalanced mass from axis of rotation. The key concept here is force transmissibility, denoted by T suffix R, that is, the ratio of force transmitted to the foundation to the excitation force. Here, this slide provides several equivalent expressions for T suffix R. It starts with F suffix T divided by F naught, which is further expressed as F suffix T divided by M E omega squared. This is then simplified to F suffix T divided by M E R squared omega sub n squared, where R is the frequency ratio and omega n is the natural frequency. Finally, this slide here we are getting the expression, that is f of t divided by m e omega squared, which is then further equal to, in terms of r square, square root of multiplied with 1 plus bracket 2 zeta r bracket square divided by square root of 1 minus r square bracket summing up with 2 zeta r the whole square. This equation allows us to analyze the force transmissibility in a system with rotating unbalance. They show how the transmitted force depends on the frequency ratio, damping ratio, unbalanced mass, eccentricity. By manipulating all these parameters, we can design vibration isolation systems which can effectively reduce the transmission of vibration caused by rotating unbalance. Let's consider a more complex scenario, a vibration isolation system with flexible foundation. Unlike our previous example like rigid foundation, Here the foundation itself can move. This adds a degree of complexity to our analysis. Here we see that vibration isolation system with flexible foundation. This means we are dealing with system where the supporting structure is not perfectly rigid and can exhibit motions. The diagram illustrates this concept. We have a machine represented by mass m mounted on a flexible foundation represented by mass m2. The machine is connected to the foundation by an isolator represented by a spring with stiffness K. The machine is subjected to a force of F of t, which is equal to F naught cos omega t. If the foundation moves, the system has 2 degrees of freedom. This means that we need two conditions to describe the motion of the systems. That is x1, the displacement of the machine, x2, the displacement of the foundation. The equations of motions are m1 x1 double dot plus k times x1 minus x2 equal to f naught cos omega t. And the second equation is m2 x2 double dot plus k times x2 minus x1, which is then further equal to 0. These equations are derived using Newton's second law and represents the dynamic equilibrium of the system. Then we are assuming a solution of the form, that is x of j equals x suffix j cos omega t, where j varying from 1, 2. This means we are assuming that the displacement x of 1, x of 2 are harmonic functions with the same frequency as the excitation force. X of 1 and x of 2 are the amplitude of the displacements. Substituting the assumed solutions into the equations of 1 and 2, we may further simplify the equation, and the expression is stated here. This equation allows us to analyze motion of the machine and the foundation in a system with a flexible one. By solving these equations, we can determine amplitude of the displacements and understand the system response to the excitation force. Let's delve deeper into the analysis of vibration isolation system with flexible foundation. This slide focuses on determining natural frequency of the system and the steady state amplitude of the machine vibration. As we discussed in this previous slide, this system has 2 degrees of freedom because the foundation is flexible. This means we need to find two natural frequencies to fully understand the system's dynamic behavior. Natural frequencies are given by these expressions where one of the natural frequency is 0. It is we already seen in our 2 degree of freedom systems. Thus, once again, we can able to solve this equation and we can able to find out the natural frequency of omega 1 and omega 2. Here omega 2 represents the vibratory mode where the machine and the foundation oscillates related to each other. This equation allows us to determine the amplitude of the machine vibration at steady state for a given excitation frequency. We can understand how the system responds to different excitation frequencies and how the system parameters affect the amplitude of vibrations. Let's continue our analysis of the vibration isolation system with a flexible foundation. Here, we focus on determining amplitude of the foundation vibration and force transmitted to the supporting structure. The system has 2 degrees of freedoms because the foundation is flexible. Therefore, we need to analyze motion of both machine and the foundation. Let me see the amplitude of mass m2 is given by this expression, and then The force transmitted is going to be given by using this expression. The significance is this equation allows us to determine force transmitted to the supporting structure at steady state. Minimizing this force is the primary goal of vibration isolation. By analyzing this equation, we can understand how the system parameters affect the transmitted force and how to optimize the system for effective isolation. Now, let's analyze the transmissibility of the isolator in our vibration isolation system with a flexible foundation. Transmissibility, as we discussed, is a crucial metric for evaluating effectiveness of the isolators, which is shown in mathematical way and expressed here. It may be further simplified in terms of masses and K, and further it is rewritten in terms of natural frequency to the forcing frequency ratios. And from this, we can able to see that the transmissibility of the isolators, where omega 2 is the natural frequency of the system, Ft decreases as omega 2 decreases. Now, let's work through a practical example to apply the concepts what we discussed. This problem involves designing a spring support for an exhaust fan to minimize the transmitted vibrations. The problem states an exhaust fan rotating at 1000 rpm is to be supported by 4 springs, each having a stiffness of K. If only 10% of the unbalanced force of the fan is to be transmitted to the base, what should the value of K? Assume the mass of the exhaust fan to be 40 kg. So we are given the following information, that is rotational speed of the fan. Fan is supported by 4 springs. Desired transmissibility ratio, that is 0.1. Mass of the fan, that is 40 kg. To solve this problem, we need to follow some steps. That is, first we calculate the excitation frequency. Next we use the transmissibility equation, and then we solve the stiffness. Let's calculate the excitation frequency omega. Omega is equal to 2 pi divided by 60. Substituting n here, that is, we have to get it from the transmissibility ratio. Substituting it, we can able to get the omega in terms of radians per second as 104.7. Next, we need to use transmissibility equation. Since we are dealing with the rotating unbalance, we will use the equation. We can rearrange this equation to solve for omega 2. Now we know that omega sub with respect to n equals square root of K divided by m. Since we have 4 springs, the total stiffness for K is given. Therefore, omega of natural frequency equals the square root of 4K divided by the mass, that is 40. Substituting these values, we will get natural frequency in terms of K still. By substituting this omega n in the transmissibility that we know already given in the problem, it is 0.1. The only unknown will be become as K. By solving and simplifying this further, we can able to get the stiffness of the system is going to be 9969.6 Newton per meter. Now, let's work to another example to solidify our understanding of vibration isolation. This problem involves designing an isolator for a stereo turntable to minimize the transmitted vibrations. Problem states a stereo turntable of mass 1 kg generates an excitation force at a frequency of 3 Hz. If it is supported on a base through rubber mount, determine the stiffness of the rubber mount to reduce the vibration transmitted to the base by 80%. So we are given the following information. The mass of the turntable is 1 kg, excitation frequency is 3 Hz, Desired vibration reduction is 80%, which means the transmissibility is zero point 0.2. To solve this problem, we need to follow some steps. Calculate the excitation frequency in cycles per minute, that is CPM. Calculate the desired static deflection, that is del static. Then calculate the stiffness of the rubber mount. First, calculate the excitation frequency in CPM. Let's calculate the excitation frequency. We know that F is 3Hz, which means 3 cycles per second. To convert this into CPM, we multiply by 60. That is 3 Hz times 60 seconds per minute equals 180 CPM. Next, we need to calculate required static deflection. For that purpose, we use the formula n equals 29.9092 times the square root of 2 minus r divided by delta substatic times 1 minus r. From this, the known is going to be the del static only. R is known, n is known, that is 180 CPM. We can substitute and find the del static is nothing but 0.1657 meter. Further, using very simple calculation, the del static equal to mg divided by k. Del static we know just as a derived. Mass is given, gravity 9.81. We can able to calculate the stiffness by the known values. Therefore, for the stereo turntable, k equals to 59.217 newtons per meter. That is, this is the stiffness of the rubber mount. It should be approximately 59.2179 newtons per meter. This example demonstrates how to apply the vibration isolation to design an isolator for a stereo turntable. Let's work through an example that focuses on determining required damping ratio for vibration isolation. This problem involves limiting the transmissibility at resonance. Vibrating system is to be isolated from its supporting base. Find the required damping ratio that must be achieved by the isolator to limit the transmissibility at resonance. T transmissibility equal to 4. Assume the system to have a single degree of freedom. So we are given the information, that is, system is a single degree of freedom system. Desired transmissibility at resonance is 4. To solve this problem, we need to follow some simple steps. Use the transmissibility equation at resonance and then solve for damping ratio zeta. Let's do it. By solving that, we can able to get the transmissibility equation. From that, we can able to find out the zeta, that is 0.1291. From that, we can further extend and calculate what is that required amount of natural frequency or masses, anything we can able to identify from this. So this is a very simplest problem we already solved, that is the damping ratio is 0.1291, which is very much essential, that is the required damping ratio to achieve the isolation according to this problem. Now let's consider a more realistic scenario, vibration isolation system with a partially flexible foundation. This is a step closer to real world applications where foundations are neither perfectly rigid nor perfectly flexible. The slide clearly states vibration isolation system with partially flexible foundation. Base of isolator is partially flexible as shown in the figure. This indicates that the supporting structure has some flexibility, but it is not as idealist as a fully flexible foundation. The diagram illustrates this concept very clearly. We have a machine represented by mass m mounted on a partially flexible foundation represented by mass 2. The machine is connected to the foundation by an isolator represented by a spring with stiffness K. The machine is subjected to a force F of t, which is equal to F naught cos omega t. This slide also introduced the concept of mechanical impedance at base. It is Z omega. It is defined as applied force of frequency omega divided by displacement. This impedance represents the resistance of the foundation to motion at a given frequency. It is more general way to characterize the foundation flexibility compared to simply using the mass and stiffness. Let's shift our focus to active vibration control systems. These systems offer a more sophisticated approach to vibration isolation compared to passive systems what we discussed earlier. Here we clearly states that is this is nothing but active vibration control, which is shown in this figure, which is a schematic arrangement. This indicates that we are going to examine how an active system works to control vibrations. Here in this diagram, see the key components of an active vibration control system. We have a mass subjected to an external force F and experiencing a displacement x of t. The system includes a passive component represented by a spring K and a damper C. However, the core of the active system lies within the dashed box, which is labeled as active control system. Inside the active control system, we have a motion sensor, signal sensor, which controls that the process and calculates necessary control action, an actuator that applies a control force based on the control signal. The key to active control is the feedback loop. The sensor measures the vibration, computer calculates the control action, and the actuator applies the force to counteract the vibration. This loop is continuously operates to minimize the vibration. Passive system provides some inherent vibration isolation. Active system enhances this by actively intercounting and absorb the vibrations. Active vibration control offers key advantages. It can achieve higher level of vibration isolation compared to passive systems. It can adapt to changing vibration conditions. It can control vibrations over a wide frequency range. However, active systems are more complex and expensive than passive systems. So, in this slide, we completed the working principle of active vibration system. Let's delve deeper into the characteristics of active vibration control systems. Here we are focused on the fundamental principle and the different types of components used in these systems. Let me see. The system maintains a constant difference between vibrating mass and the referee. The highlights core objective of active vibration control. The system aims to keep vibrating mass at a fixed position related to a reference point, effectively cancelling out the vibrations. The term referee may seem a bit unusual in this context. It refers to the reference point or frame of reference that the system uses to determine the desired position of vibrating mass. It could be a fixed point in space, a desired equilibrium position, or even a moving reference point depending on the application. So, depending on the type of sensor, signal processor, actuator used, the system can be electromechanical, electrofluidic, electromagnetic, piezoelectric, or simply fluidic. There, we highlighted the versatility of active vibration control system, specific component used to determine type of system and its performance characteristics. Electromechanical systems use mechanical components like gears and levers along with electrical sensors and actuators. Electrofluidic systems use fluids to transmit forces, offering high force capabilities and bandwidth. Electromagnetic systems use magnetic forces to control the vibration, offering high precision and fast response. Electro, that is, piezoelectric system use piezoelectric materials that generates voltage when deformed or deformed when a voltage is applied, offering very huge potential, that is, it can able to control precisely this precise control of the systems. Fluidic systems use fluid logic to control vibrations, offering robustness and reliability in harsh environments. The choice of component depends on the specific application requirement, such as the frequency range of the vibration, required precision, and the operating environment and the cost. So, the fundamental principle of active vibration control, maintaining a constant distance between the vibrating mass and a reference point. This type of system depends on the specific component used, offering a wide range of options for different applications.